Good afternoon, everyone. I'm Hongyi from Sustech, and in this talk, I will present my work titled MOAT towards Safe BPF Kernel Extension. This work is finished jointly by Sustech and HKUST. So first, let's go through some background about eBPF. To begin with, what is eBPF? Its full name is Extended Berkeley Packet Filter. Despite the name, it is in fact a kernel virtual machine. It allows user-land programs to inject all sorts of extensions into the kernel and extend its kernel functionality in an event-driven way. It is actually based on the classic BPF in FreeBSD, and eBPF was brought to Linux in 2014. And it has changed from merely a network packet filter to full functional kernel virtual machines that plugs into all sorts of Linux subsystems from like tracing, networking, and for security purpose. The follow-up question is why to use eBPF? Given that kernel module can basically do everything that eBPF can do, why not someone just write a kernel module instead? The first reason that is fast. eBPF by default runs in JIT native machine code, which gives it equivalent performance comparing to kernel modules. The second reason is that unlike kernel modules, which lacks the portability across different kernel versions, eBPF enjoys the benefits from a set of stable kernel API named helpers and is able to compile once, run everywhere. Most importantly, a lousy eBPF program does not randomly crash your kernel, unlike a lousy kernel module. There is a verifier deployed that rejects any badly written eBPF program from running in the beginning. Yes, it's upsetting when your BPF program is like rejected for like 30 times in a row, but at least you don't need to spend 30 hours to debug your kernel module. Despite all these disadvantages, eBPF still have a major flaw, its security. eBPF solely relies on the static checks conducted by its verifier, which is insufficient for such a critical kernel component. There were over 20 arbitrary read and write kernel vulnerabilities appeared in the BPF subsystem over these years, and there are mainly two reasons behind this issue. The first is that the static analysis conducted by the verifier is inherently hard. No matter how hard we try, it's very hard to balance the soundness and the completeness of the verifier at the same time. Not to mention, the verifier is deployed inside kernel with many other factors to consider. The second reason is that eBPF itself is also undergoing rapid development. It is expectedly messy that every time a new feature is introduced in BPF, and the verifier must add a new corresponding verification for that. And things may just go missing and wrong between the implementation of the verifier and the implementation of BPF itself, especially when they are maintained by different people, leading to all sorts of vulnerabilities. We therefore propose our work, MOAT. We used hardware features like Intel MPK to isolate BPF programs from Linux kernel. Moreover, we also resolved a set of domain-specific challenges, like how to overcome the limited number of MPK tags and how to protect BPF APIs. You may ask, what is Intel MPK? Essentially, it just adds a 4-bit tag to each page table entries, and from 0 to F, so there are a total of 16 tags. And with this tag set, you can toggle the page permissions at once if all these pages have the same tag. Comparing to setting these PTEs one by one, it's much more efficient to use MPK to change them all at once. With all these ingredients, we will introduce our isolation method in details. Despite being efficient, MPK has only 16 tags. It's far from sufficient for multiple BPF programs. So once you have over 16 BPF programs loaded to your kernel, you don't have enough keys to isolate them one by one. But it's abundant for setting up isolations between just kernel and all BPF programs together. So we follow up this design by setting up 3 different domains: kernel domain, BPF domain, and the shared domain. The first one is the kernel domain. It comprises all the kernel data and code. The second domain is the BPF domain. It contains all BPF programs together. When a BPF program is running, MOAT enables the BPF domain and disables the kernel domain to prevent any unauthorized access from BPF program to the Linux kernel. Lastly is the shared domain. It contains structures like descriptor tables. Both BPF program and the kernel need this for low-level routine like interrupts, so we set it as read-only. By this 3-domain design, MOAT successfully protects kernel from evil BPF programs. However, this design still puts all BPF programs together, allowing a malicious BPF program launch attack on the benign ones. So we resolve this issue by giving each eBPF program its own address space, just like the figure shows here. And if a BPF program tries to tamper with other programs, it will only result in a page fault. But there is still one issue remaining, the TLB flushes. The TLB overhead can be huge if one switching between address spaces frequently. MOAT resolves this issue by 2 methods. Firstly, thanks to the 3-domain design, we can safely keep the MPK protected kernel memory as a constant mapping in all address spaces without kicking them out during the address space switching. This significantly reduces the TLB overhead as BPF has much smaller memory footprints comparing to the kernel itself. Secondly, we use process context ID to track the page table entries used by BPF programs and avoid unnecessary flashes when the switch occurred between BPF program and the kernel. The above-mentioned design handles the memory safety of all BPF programs well and efficiently. Yet, BPF can still access the kernel via a set of its APIs named the BPF helpers, which could become potential attack surfaces from BPF to the kernel. MOAT does 2 things to mitigate this risk. The first one is that we isolate the kernel structures that are easy to exploit from the view of helpers. The second is that we check parameters against the set of verified bounds. Now let's go through these 2 methods in detail. By studying previous BPF CVEs, we are able to identify kernel objects that could be potentially exploited by BPF programs. In total, we identify 44 of these objects. We refer them as critical objects. And MOAT starts allocate an extra MPK tag for them and set up an additional domain. This extra MPK tag allows MOAT to change the permissions in a finer grain. In this way, MOAT can prevent helper access to these critical objects, as these structures shall not be read or write by a helper in the beginning, in any case. On the other hand, MOAT still grants access to helpers to other kernel objects so that BPF helper API can still function normally for the programs. MOAT also uses verifier spawn to double-check helper's argument during runtime. You may be wondering why the verifier becomes trustworthy suddenly. Are we assuming there are bugs in it? The case is that BPF verifier provide bad statically deduced value about a variable range, about a variable value, and that's the main source of bugs. But the verifier always provides sound bound for the valid argument ranges. In practice, we observe that the bounds provided by the verifier is always valid, and in all CVEs we found and studied, the case is that the verifier makes a wrong static deduction about the variable value. By directly comparing to the actual runtime value to the bounds provided by the verifier, MOAT ensures the validity of helper arguments to a great extent. Lastly, let me introduce our evaluation results. So for security evaluation, we verified that MOAT is able to mitigate all 26 BPF CVEs within MOAT scope. Now let's go through one in detail. In this snippet, the first two lines is just loading two values. R5 is an attack-controlled address, while R6 is a large constant. The lines 3 and 4 helped verifier to deduce the value of R5. Basically, the verifier believes that if the program did not exit on line 4, then the value of R5 must be larger than 0 and smaller than the magic constant. What's interesting here is the line 5, where R5 is OR 32 with 0. The verifier conducts a wrong truncation and clear the upper bits of its deduced value. Thus, the upper limit of R5 is certainly become 1, and the verifier believes the R5 is a constant 1. Such gap then becomes a vulnerability in the verifier, since the verifier believes R5 is a constant 1, and then R5 is allowed to serve as a legitimate offset in memory access, but is in fact an arbitrary value that is controlled by the attacker, resulting in an arbitrary read and write primitive. Fortunately, MOAT can effectively stop such exploitation by constraining all BPF programs to its own domain. Such attack attempts will only result in MPK violation. We also conducted a detailed performance evaluation in all mainstream use cases of BPF programs. MOAT shows great performance in all use cases. In network filtering, the throughput loss is less than 2%, even if when we run 5 different BPF programs at the same time. In system profiling, we load 11 BPF programs to profile all sorts of kernel metrics and run Unix bench with all these BPF programs attached. The maximum overhead is under 13%, and the average overhead is only 6%. And MOAT's overhead is also low for system core audits, with only 3% performance loss when we're auditing all the system cores of an NGINX server. We also compiled MOAT with software-based solutions like StandBPF, which is the previous work in BPF isolation, and more where we stress MOAT with over 100 BPF programs running in parallel. The overhead is still less than 10%. Here are some takeaways. BPF is a thriving ecosystem, but its security is a concern during its growth. And MOAT shows that BPF security can benefit from hardware features like Intel MPK, and by combining software and hardware, MOAT successfully secure BPF programs in both memory and its API usage. Thank you very much. I'm ready to take any questions.